Welcome ENGR ampersand 214, otherwise known as Engineering Statics at Bellingham Technical College. This lecture is about moment. We're going to start with moment about a point and we're going to end with moment about a line. Moment is also known as torque, or a rotational analog to force. So we're going to define moment with words, and then we're going to use our friend vector algebra to define it using a cross product. Okay. So we're going to start with moment about a point. If you got a force vector hanging out there in space and you have some point of interest, like maybe it's a pin and hanger on a bridge or some corner or part of something you're designing, and you don't want it to rotate, you're going to want to know what the torque is that's applied to it so you can appropriately constrain it. So you're going to want to know what the moment is about that point due to some force that you know is being applied to your 3D body. So you're going to want to know the moment of that force about your point. Okay, well, it turns out moment about a point is a vector, not surprisingly. It's got a magnitude that's equal to the magnitude of the force that's responsible for it times the perpendicular distance from your point of interest to the line of action of the force. Only the perpendicular part. That moment vector is going to be oriented perpendicular to a plane that contains both your point and the force line. And it's going to be oriented with a direction given by the right-hand rule. That's a lot. It's a vector. It's got a magnitude that it's equal to the magnitude of the force causing it, and the perpendicular distance from the point you're looking at to somewhere on its line of force. It's going to be one point on that line. It's always going to be perpendicular to the plane that contains your force line and your point, and it's going to have a direction, or a direction that it would cause rotation in, clockwise, counterclockwise. It's given by the right-hand rule. It's a lot easier to express all of that with a vector algebra product. So here's the same thing written twice using vector algebra. So we have a capital M sub p with an arrow over top, meaning the moment about point P, and it's got an arrow telling us this is a vector. This is equal to the cross product, or the vector product, of the radius vector going from point P to any spot on the line of force of F. So that's where the PF subscript is, from point P to somewhere on the line of force F. It's a vector, of course, and your force vector. Very important, from the point to the line of force. This is hardwired in the definition of moment, not the other way around. Why is direction important? Because it's a cross product. So if we get the direction on the radius wrong, we're going to end up torquing it in the wrong direction, clockwise instead of counterclockwise, and vice versa. So we cross our radius vector into our force vector, and that's the definition of moment. So we can evaluate this cross product with a determinant or with our FOIL method that we've used before. If we want to look at it geometrically, we know that our cross product, of course, is equal to the magnitude of our two vectors times the sine of the angle between them. Remember when we said something about perpendicular distance from the force, the point we're concerned with, to the line of action of the force? Well, it's our cross product that takes care of making sure we only take the perpendicular portion of that radius. So that's where our sine theta comes in, the angle between the two vectors. So let's look at this with a little quick sketch. We got this point here somewhere in space, and we got a force vector that has an associated line of action with its dotted line. So our definition of moment says that the moment about this point, due to this force, the turning about this point, or torque about this point, is going to be this radius vector r, which goes from the point to this particular spot on the line of action of the force, crossed into the force vector. So let's take this geometrical definition. Okay, we kind of extend the line of action in both directions so we can get the acute angle between the radius and the line of action, and here it is, here's theta. So our crossed into that, we're going to take only the sine of that. So if this is theta, here's the hypotenuse, here's the adjacent, here's the opposite. Sine r, the magnitude of r, that distance, times sine theta automatically gives us this perpendicular. So our opposite in this particular little right triangle is automatically the perpendicular distance from the point to the line of force. So the cross product gives us that perpendicularity. And some of you have taken physics, have probably looked at torque as being force times distance, but it's always force times only perpendicular distance. So here we get to look at all kinds of different force vectors, and we get to use the cross product to take that perpendicular portion only. Okay, so let's put our vector algebra that we've worked so hard to learn, hopefully by this time, and let's put it to work to give us different ways to evaluate moment, because sometimes one way is easier than the other. Let's use a distributive property of the cross product to allow us to say that the moment of the sum of the forces is equal to the sum of the moments due to each force acting alone. Wow, that could be really useful if we've already combined all of our forces into a single equivalent resultant. We just get its line of action, make a radius vector from our point of interest anywhere on that vector, and evaluate the cross product, and we'll have a torque or a moment. Okay, so here's an example of where you might want to use that. There's somebody's got a box here, it's sitting on the floor, and they've got a point here where they've attached a couple of ropes maybe, so they're pulling upwards with a force of F1 and then a little bit downwards from horizontal with a force equal to F2, a couple of ropes. We could combine F1 and F2 and get a sum. So F sum is equal to that vector sum. So that's the net force being applied to point A. If we're concerned about whether or not we're going to topple, we're going to cause this box to start turning over point P instead of maybe sliding along the floor like we'd like, we'd be interested in knowing what the moment is about point P, about this very corner edge. And in fact, this is something we'll explore in friction, or you might explore in your course on friction, where you look at sliding versus toppling criteria. So the moment about that corner point becomes very important. So it's great we could calculate it. Well, we can take the moment due to the sum of the forces, so we can just use this sum vector as a single vector. Well, that vector, that force vector, goes through point A, so point A is a point on the line of force. The point of interest is P down here, so we can draw a radius vector from P to some point on the line of force of F sum by just drawing a line straight up, or whatever direction the front of that box is oriented at, R. And we've already evaluated F sum and put it in vector notation. We know what direction R is pointing, as presumably we know the dimensions and the contours of the box. So we can evaluate the cross product, no problem. If for some reason we didn't have that sum and we needed to say evaluate two moments, or maybe one of those ropes was going to stay fixed and we had to slacken off on the other one, and so we wanted to get the moment due to this rope F1 and this one separately, because maybe we wanted to change them or something like that. So then it might be good to evaluate moment as an individual contribution of each force. No worries. We can just do some math and prove that it's okay to evaluate them separately, and we come up with the same thing. So we know that F sum is equal to F1 plus F2, vector addition, and we know that the cross product is distributive over addition. So we can just literally distribute this cross product multiplication, R cross F1, R cross F2. We can make this equality, and of course R cross F1 is the moment due to F1, and R cross F2 is the moment due to F2. So we could change either one of these forces and then get a separate idea of how they would contribute to the overall moment. So have a little bit of an example that we can work through. This is a little bit light, so I'll walk you through what we see here. This is an arbitrary coordinate axis. Here's the origin. We got the y-axis. This would be the j-hat axis, and x, the i-hat unit vector direction. And so we have a couple of points of interest. Point B up here on the y-axis, it's 12 meters up, and point C is 16 meters over on the x-axis. And there's some point A out here at 4 meters horizontal, 9 meters vertical, and it sits on a line of action of a force of 10 newtons that connects, and the line of action connects points B, A, and C. So if you draw a line between those 3 points, it should you should get them all on a line. You can check your line equation and make sure it is. But the force vector is definitely pointed along that line of action. And so we can ask ourselves, what is the moment due to this force, that's force A, because it goes through point A, around the origin? So this is the way we would write that. We've got a capital M here with a little arrow saying, hey, I'm a vector, I'm a moment vector. Capital M, by the way, is typically used to denote moment. Writing torque, which is the same thing, you use a little Greek letter lowercase tau. You'll usually see capital M here in statics. So this is capital M due to A about point O. So just seeing the subscripts tells you kind of what's causing it and what the point of interest that we're turning around, or trying to prevent things turning around, because this is statics, nothing's going to move. We just got to make sure it doesn't. We're going to see what the moment is that's applied, and know what counter moment we would need to have from a constraining structure, for instance. So we need an R and we need an F, and we did them both in vector form. Okay, so I want the line of action of the force. I got a magnitude in newtons. So now I need a pure direction. Sounds like I need a unit vector. Well, that's easy. I know the line of action goes through, if I wanted to denote the line of action, I could write it as the sum of a vector going from the origin to B plus a vector going from the origin to C. With, of course, actually it would be from B to the origin. Gotta have, it's going, the arrow's pointing down. Apologies. So I can write a unit vector that's the 16 I hat, so it says, okay, go over 16 and then go down 12. Over 16 and down 12. That's the actual direction. Of course, now I'd have a bunch of length in it, and I only want force for this part of things. So of course I square 16, square 12, add them together, take the square root, and end up with 20. So I'm going to divide out that length. So this portion that I'm kind of outlining with my mouse, hopefully you can see, is the unit vector portion of it. And then I multiply by 10 newtons, and I get a force vector of 8 newtons I hat minus 6 newtons J hat. And if I wanted to confirm that it indeed was 10 newtons magnitude, I could square each of these atoms. I get 64 plus 36 is 100, square root's 10. Yep, good. That tells me I did my unit vector right. So I'm going to use this in a cross product, and now I just need a radius. Well, I could work really hard with geometry and actually try to get a true perpendicular, or I could use a cross product and say, just give me a point anywhere on that line, and I'll use the cross product to make it perpendicular. That tends to be my favorite because I don't like trying to envision complex geometry. I think it's easy to make a mistake. If I know what the points are and I execute a vector product properly, I know I'm going to get the right answer. And of course, you got to execute it properly. So of course, it's always possible to make mistakes. And you can always use a geometric method to check your vector algebra and vice versa. If you're working on a team, maybe have half the people do it one way and half the people do it the other, and you should get the same answer. So in this example, I picked the radius vector from the origin to point B, because point B is on the line of force. So that vector would simply be 12 meters J hat. And units are important. because, as everybody knows, moment and torque are not in newtons, they are in newton meters, right? Because you're keeping, let's go back up to the definition, you're keeping the magnitude of the radius and the force. So radius is going to be in length and force is going to be in force units. So newton meters, foot-pounds, things like that. So it'll be length times force. Keep your units with you in your calcs, and that's another way to see if you've made a mistake. If you're doing a graded assignment and you note that you've got a units discrepancy at the end of a long string of calcs and you suspect there's an error, quite often instructors might be a little kinder with partial credit. Certainly it will give you an idea not to let work out to a client or to your boss if you know there's an error in it. So it's an easy check. So I'm going to apply the cross product two ways. First, I calculated algebraically what the angle theta was here, just using some points to get my lengths, my adjacent and opposite, and trigonometrically I was able to get 53 degrees as alpha, so I could plot that into the geometrical definition of the cross product, and calculated a moment due to force A around the origin of 96 newton meters into the paper. So I used the right hand rule. I extended my fingers from the origin towards point A, and then I curled them around in the direction that this arrow is pointing, and my thumb was pointing into the paper. So it's my thumb is into the paper, and so that would also be, you could consider that to be a clockwise moment. I can also do the cross product, and here I use a little determinant. So I did R cross A, and I used R as 12 meters j hat. So here's 12 meters j hat written on my first line. So this is the determinate method of the cross product. I do my first vector on the top and my second one on the bottom. And this should actually be a -6 here. And the math worked out. I got a negative 96 newton meters k hat, and so of course the k hat says it's going in or out of the paper, and the negative means it would go into the paper. So that's the two different definitions or expressions of the cross product, getting me my moment due to the force A about the origin. So a lot of things will look a lot like that. Got something very similar here. We were given a radius P to Q. So there's a radius vector here from point P to point Q somewhere on this line of force. Somebody threw the radius vector out in 3D. Maybe they did a coordinate measurement system, or they did a survey or something. So we had this point, we knew where it was, these 2 points, and so we could get a vector between them. And then we knew a line of force. We had this from some other measurement. We knew what the applied force was, what direction. How would we find the moment of this force around point P? Easy. We got a radius vector, we got our force. Q is on the line of force, so all we have to do is cross this R into this F. Just literally apply the definition of moment. And I worked this out. Instead of foiling it, I used the determinate method again. This is another method of evaluating a cross product. You can find this in your vector algebra reviews. Again, I'll recommend Khan Academy as an excellent source, both to teach you how to evaluate cross products and also how to interpret their geometric meaning. But for this determinate method, you just basically create a matrix that includes your coordinate axes on one line, and to make it easier to write out, you just repeat the first 2 columns. You put your first vector to be crossed, which is of course to calculate moment always going to be the radius, on the next line, and repeating the I and J, and then force on the last, and then literally multiply along diagonals. And then when you go from left to right, it's positive. When you go right to left, you put a negative sign outside of the whole group of terms. So in this case, I would have 3 times 5 times I hat to give 15 I hat. Then I'd have -4 times 1 times j hat. So there's -4 j hat. 2 times negative 2 times k hat, so that's negative 4 k hat, all of this with a positive. And then I evaluate going on my other diagonals, so I have k hat times 3 times 1 inside here, and then I have negative 4 times negative 2 is 8 I hat right in there, and I have 2 times 5 is 10 j hat right in here, and if all of this gets a negative sign, I hats get added to I hats, j hats get added to j hats, k hats get added to k hats. So we have negative 3 k hat plus negative 4 k hat should be negative 7. I have negative 10 j hat plus negative 4 j hat should be negative 14 j hat. And then I have negative 8 I hat, and 15 I hat should give me a total of 7 I hat. So here's my moment vector. No idea which way that's pointing. Don't have to. That would be its vector expression. And given that everything else was in coordinate vector expression, this is totally appropriate for determining the torque due to this force about this point. We could use this to do an analysis then about how to construct restraining structures, or if this were a dynamics problem, we would have the input for alpha rotational acceleration if we wanted to get something spinning, which we're not going to do in statics. We're going to keep it still. And given that it's not in a straight line, it can't even be moving at the same velocity. It's got to stay still. Okay, we got another kind of vector algebra problem that I'll let you guys go through on your own, since it's pretty redundant with the other two. And we're going to jump ahead to moment of a force about a line, okay, as opposed to a point. So literally, we could just apply the cross product, boom, definition of, to get the moment of a force about some point. All we have to do is make a radius vector from the point to anywhere on that line of force, and then cross that radius into the vector expression for the force. Okay, well, as it turns out, that's the first step for finding the moment of force about a line, okay? Because the first thing we'll do is calculate the moment of that force about some point anywhere on the line. Then we're going to take the portion of that moment vector, this is just a vector, and we're going to find out what portion of that moment vector just happens to be parallel to a unit vector that represents the direction of the line. Now remember how dot products give you the portion of something that's parallel? So we're going to calculate the moment of the force about any point on the line, anywhere convenient, anywhere we happen to know a point on that line. No problem. R cross F. We got a point on the line that we're interested in. We know the direction of we have a vector expression for our force, R cross F. We got the moment. We got a vector expressing moment. We can get a unit vector for the line that we're interested in. Easy. We'll have some, it's a vector. We got some way to figure out some magnitude, divide it out, get an L hat, unit vector in the direction of the line, and just dot that into what we just got for the moment about any point. Because we only want the point, the portion of that moment about the point on the line that happens to be parallel to the line. Okay, so not all of the moment about this point P on this figure here happens to be parallel to L. It's only the portion of this M sub P that would be given by the cosine of the angle between. Cosine of the angle between, there's your dot product. Okay, so the literal definition of the force about a line, so that's capital M sub L, meaning moment about a line, little arrow reminding us it's a vector, is equal to the vector moment about the point dotted into the unit vector for the line. And then of course if you want it, this will actually, because it's a dot product, this will give you a magnitude. Then we have to go dot that again into the unit vector for the line to give it an actual direction. But the M sub P dot L hat gives us this cosine relationship here. So it allows us to select the bit of M sub P that's parallel to L hat and therefore constitutes m sub L. Where would we use this? When we want to know the torque around a shaft, not just a point on it, but the turning force of a shaft. That's its main application. So like a screw that's turning, or any kind of rotating shaft motor. We might know the moment about some point, like maybe an individual point on the bearing. So this would maybe give us the moment that's trying to turn the shaft in its bearing. Not so good. Make it flex in the bearing versus the moment that's actually causing it to rotate as we want, supported by the bearing. So different directions of moment. Okay, we can actually do some proof of that dot product. It looked pretty obvious, but we can actually go through a little proof here just to practice our vector algebra if we wanted. And it turns out that we prove it with some vector addition. So I will step through this with you just for some good vector algebra practice. You will only use this in statics if you have your forces and your points and lines of interest as points. Again, if they're coming out of a coordinate measurement system or a point cloud from a survey. That again is becoming more and more common in engineering. So, going back to these real fundamentals of vector algebra it's becoming more and more useful, especially because these types of vector operations can be programmed into a computer. So if you're doing force analysis, specialty analysis with matrix methods, maybe with Octave or something, and you're writing yourself a little program to do analysis, these are the type of concepts that you might use as the basis of your programming. So definitely worth taking a few minutes to just step through here. So, and it's good for the mind thinking about forces. So we're going to prove that m sub L is in fact the turning force of F about line L. So we're going to prove that our dot product m sub L is actually equal to the true perpendicular distance of this force versus this point, and will produce the actual turning force of what would be a shaft in the direction of this line. Okay. Well, the first thing we could say is that's the same as saying the moment of this force about, say, some point P, the magnitude is going to be the same as moment of point P dotted into our unit vector for our line. I mean, that's the argument we just gave as the definition of m sub L. And more intuitively, we would think of this as the moment of this force about point A, which we know is perpendicular to the line of action of the force. That's our more intuitive definition of torque of a force about a shaft. It's got to be perpendicular. The line of action of the force has to be perpendicular. So we're really showing that the perpendicular part is going to somehow be taken care of in this definition. Okay, so we're going to say the moment of F about any point on line L will have the same magnitude component of the component parallel to line L. So that's what we kind of have to prove in order to make this true. So we go through a few steps. This is like doing proofs in geometry. So can we really say that the moment about point P on the line dotted into the unit vector for the line is the same as A? So does it matter where you are on the line, basically, or does the dot product somehow take care of it for us? Well, as it turns out, it does. We'll go through some steps here. So we rewrite our two moments in terms of their definitions. We start by doing that. So instead of saying just m moment of F about P, we say, okay, well, how would you get that? Well, I know the moment of F about P is R from P to some point Q on the line of force cross F. There's the definition of moment about P due to F. Okay, I'll do the same thing for the moment about A due to F. I'll write it the same way. radius vector from A to that same point Q on the line of force, cross F. Okay, this has to still be true. This definition of moment in both cases. Okay, so maybe I could look at a relationship between these two radii vectors and see if there's another way to write them. Well, it turns out I can use vector addition to say, sure, of course there's a relationship. I can just go, I can use vector addition in this little triangle. So I can say the radius vector from Q to A, so I can go from Q to A or from A to Q, you can see here, is equal to going from A to P and then going from P to Q. It's the same thing because it gets me to the same place. Well, I can substitute part of that in here. So I'll do that. So now I've substituted in RAP plus RPQ for RAQ. Just simple vector addition right there. Okay, oh hey, and I can go ahead and I can distribute my cross product because that's totally allowed. So I'm going to make it easier for myself. And so now I've got RAP cross F plus RPQ cross F, whole thing dotted into L, and over here I've just got RPQ cross F. Wow, well, you know, I can distribute the dot product as well. So let's do that. And lo and behold, I now have a couple of terms that are the same on both sides. And remember, my whole intent was to show that this left side equal this right side. So can I actually rearrange it to show that they're the same? Well, at first glance, it's not looking pretty good because I've got this term here and this term here, and they're the same. I got this extra term. Well, shoot, on first glance, it looks like I just proved it wasn't true. Bummer. It would be really nice if this were 0. Maybe I can get away with that. Let's take a look. What would it take to make this cross product 0? Well, RAP cross F, you know, this is the same as the magnitudes of both of them times the sine of the angle between. So if they happen to be parallel, if F and RAP happen to be parallel, that would be particularly nice. Or perpendicular, I might be able to write a relationship. We know that RAP is on line L. Okay, so RAP cross F is by definition perpendicular to line L. So we're not going to get rid of that in the cross product, but we got a cosine relationship over here. So we're going to get rid of it in 2 steps. So let's look at RAP cross F. Here's RAP. It's on line L, and we're going to cross it with F. Once I do the cross product, I get something that is by definition perpendicular to line L. So when I dot it back into L, now I'm taking the cosine of something that's 90 degrees, and this term disappears. So since RAP cross F is perpendicular to line L, by definition, cross product, then when I take something perpendicular to something and dot it, excuse me, hope that didn't come through, I'm going to get 0. So it's the sine of the angle that makes it 0. So my proof turns out to be true because this term disappears, because I've basically used cross product and dot product to take a portion that's perpendicular and then say, no, I only want the portion that's parallel. Oh, nothing left. So I proved that it's true. So basically, I just proved that our kind of dot product definition of moment about a line is the same as kind of our intuitive definition of torque of a force about a shaft based on a perpendicular distance, perpendicular radius there from A to Q. So just using what we know about perpendicularity and parallel nature of dot and cross products, and then using some vector sums and some distributing of cross and dot products, we're able to prove it. So good exercise. And you can step through those yourself and just kind of go through the proof. Okay, practical definition. Moment of a force about a line. So this is just another way of looking at it. We can look at any force vector from the point of view of the line and say, well, I got a force vector. I really only care about the part perpendicular and the part parallel. And some of this might be because the part perpendicular is going to give a torque about that shaft, which might be good if I want it to rotate. The part parallel to it might say make the shaft move and slip in a bearing axially. That's really bad. So I might just be concerned with the part that can turn it and the part that can slide it along its axis. So I can take a look at just sort of resolving any vector I have in what turns and what slides. So it might be useful for anyone designing a mechanical system. So I can use these definitions to pick those different parts. And we've got, again, our line of force here. Q is a point on the line of force. And here's my shaft, line L. I got a point P1 on it. I can define perpendicular portions of this with my angle theta. So here I've got a point Q1 and a distance that is perpendicular. So I can take that perpendicular portion now, F perpendicular. The remaining is the parallel portion. So I can do all of this geometrically, or I can use my cross product and dot it and get the portion of the moment that's parallel to the line, the turning portion, and then just subtract it from the total force vector to get the remainder. So this is, I won't step through all of this, but this is another way of looking at which portions of a force are going to turn something versus make it slide, basically make the shaft slide axially along its length versus rotate. Okay. So basically a whole lot of different ways of saying the same thing. Okay, let's step through, let's see how many examples we got. A couple of examples. Let's go to one with a figure here. So this really does get into the shaft turning. So this is a socket wrench. So this is a practical machine that uses this. So we've got a bolt and we want to turn the head, and so we can look at the bolt axis is the x-axis here. So we probably want to get an idea of how much a couple or some kind of turning force that we have out here on a wrench, how much of it actually makes a moment that is parallel to the x-axis, because that means things would spin clockwise or counterclockwise around it. So we want the shaft to rotate. That means we want a moment vector parallel to the x-axis. Okay, that's easy. So we got a couple of forces. We have F1 and F2. They're both 20 pounds and they're into and out of the plane of the paper. Okay, so they're oriented, they're out here, positioned somewhere out here away from the axis, and they're pointing in the positive and negative k direction respectively, based on how we've got our coordinate axes. So k is out of the paper. So it's a 3D problem. And we want to know the moment due to both of those forces on the bolt head. So we want to know what the moment of each one of these is around that is parallel to just the x-axis. So we could use our definition of moment and say, okay, well, let's find a point somewhere on our line of interest, which is the x-axis. Well, okay, let's use the origin. X-axis contacts the origin. So let's get a moment of A about the origin, and we'll get a moment of B about the origin, and then we'll dot both of those into just I hat and add them up, and we should get something bigger than either one. As it turns out, this F1, F2 is what we call a couple. So it's like a standalone moment because it doesn't cause any net force. It only causes things to turn. So we'll learn later that there's actually a bit of an easier way to do this, but it's based on the same few steps that we'll go through. And we'll actually define a couple moment based on the same steps we'll do now. But maybe say one of these was 18 pounds, the other 20, it wouldn't be a couple anymore, so we'd do them separately. Okay, so first we got to get different radii. These forces are going in and out of the paper, and they're at different positions. So the radius vector from our turning point, a point on our axis, to A and B where the force is applied, they're different. So we got to use some geometry to get that radius. And so I'll just step through. I've already done that for you. So I started with B, point B, and I used the geometry of this right angle and this 8 inches to get a literal position of point B relative to the origin. So this is 8 inches. I was given that this shaft here is at 45 degrees. So I just used SOHCAHTOA, cosine and sine, to get its position. Positive direction is downwards and to the right. So both of these were positive directions. So there's my ROB, and with the trig functions evaluated, I got 20 pounds k hat. So F1 is pointing out of the paper, and so that's positive k hat direction. Took the cross product to get a moment of B about O, and that ended up being 113 and change inch-pounds, all in the I hat direction. So great. It's already all in the direction of the shaft. That's kind of nice. So now we'll look at A. So I had to do a little bit more geometry to get this distance. So I used the fact that this little segment AB is perpendicular to the 8 inch. And so I went from point B, and then I subtracted back the amount that would be given by this other right triangle that you can construct. So there's a lot of geometry and trig in statics, just figuring out where things are and which way they're pointing. So I could get a radius vector from O here to A, from my point of interest to the line of application, because F2 is pointing into the paper, F1 was coming out. And so my radius ends up being about 9.2 inches in the I hat, plus about 2 inches in the J hat. Let's see if that makes sense. Yeah, because it's way more down than it is over. That makes some sense. And I cross that into F2, which has now got a negative sign. Up here it had a positive sign. This is the other one that's going into the paper. And I evaluate the cross product, and I get a negative 42 inch-pounds. So it's turning it the other way. Oh my gosh. Okay, so what's my M total about the I hat? Well, I don't have to take a dot product to just get the portion of these two that are in the direction of my axis of interest, because look, both of these moments are exclusively in the direction I want. They're all in the I hat direction, so they're already completely dedicated to turning that bolt. There is no portion of it making the bolt slide in or out of the its substrate there. So I just add them together, and I end up with about 70.7 inch-pounds of torque being applied to the bolt. So you can go through the previous example, which is a little bit more dry and boring. It's all points. There's an 80 Newton force being applied through 2 points, so this gives you your line of action of the force. And there's some line of interest between 2 other points, and somebody wants to know what the moment is of this 8 Newton force about this, a line going through these 2 points. Maybe there's a shaft, or there's something they don't want to rotate. So we want to know the rotating torque. Use the same exact type of steps, except this time you're going to use all vector algebra. You won't have any opportunity to do geometry as much on this. So you'll construct your line, get its length with Pythagorean. There's your line of force, multiply by the magnitude, and get a radius from either of these points to either of these points, and calculate a moment around whatever point on the line, and You're going to need to get a unit vector for this line. So you'll start by getting a regular vector for the line. Somewhere here, yep, here's a regular vector for the line. I get its length, I divide, and now I get a unit vector for the line. And I can basically get my dot product, multiply by the unit vector again, and get a moment vector parallel, only component of it parallel to that line. So you can go through these steps on your own and use this as a self-check if you'd like. Okay, so there is our definitions for moment. Moment about a point, moment about a line, and how we use the cross and dot product to give us the portions that we're interested in. So now we will apply that in various scenarios and start adding up moments and forces together.